Okay, on this video, we are going to go over the day 2 material for the Math 136 final exam. This first video, I'll be going through problems 1 through 9, and then there will be a second video where we go through problems 10 through 19. So they're starting here with number 1 from the day 2 material. The first one asks us to find the zeros of the given function. Anytime we see that phrase, find the zeros, what they want us to do is take the function that they gave us and set it equal to 0, and then solve for x. When we have a polynomial like this, the first thing we want to try when we're trying to solve is to see if we can factor it. So when we have 4 terms like this is a good candidate to consider factoring by grouping. So I'm going to kind of chop my polynomial in half right there. And what do those first 2 terms have in common? What would the GCF, or the greatest common factor, be of just those first 2 terms? And they both share an x squared that we could factor out front. And then take a look at your second 2 terms. What's the GCF, or the greatest common factor, between those 2? And they both share a -9 that I can factor out front. When I pull out that -9, what's left behind is x plus 2. And for factoring by grouping to work, we need to get matching factors here, and we did, so that's good. Now that x plus 2 is our GCF, and we pull that out front. What's left behind is x squared minus 9. And then we can factor one more time, because now we have the difference of 2 squares. So our final factored form is going to look like this. Once we have it fully factored, we want to take each one of those factors and set them equal to 0. And it's a pretty quick solve from there. We'll just subtract 2 from both sides, and our first solution, x is -2. And then on the next one, we're going to add 3 to both sides. Our next solution is x is 3. And then our final one, we would subtract 3 from both sides, and we get x is -3. And that's kind of got all smashed together. I'll write it out here. So our solutions to this, our zeros of this function, are -2, +3, and -3. Next up, same directions, find the zeros of the function. So again, we'll set our function equal to 0. And we want to try to factor first. Is there anything we can factor here? We have 3 terms, and they do have something in common. They each have an x squared, so we can pull that out as our greatest common factor. Once we factor out the GCF, we see we can factor again in the second part. We take that x squared and we split it into x times x, and then we would be looking for factors of 45, factors of -45, that when I add them up, I will get a -4 as my result. So if I do a 9 times 5, that gives me 45. To get that -4, I need -9 and +5. So there is my fully factored polynomial. So I take each one of those factors and set them equal to 0. And then just solve each one of these little equations. So x squared equals 0. If we take the square root of both sides, we just get x equals 0. Here we add 9 to both sides. We get x equals +9. And here we subtract 5 from both sides, so -5. So our final answer, our solutions, or our zeros, are 0, 9, and -5. Okay, next up, same directions. We're getting good at this, huh? Find all the real zeros of the polynomial function. And then we're going to take one more step on this one, and we're going to use those zeros to factor this polynomial. So we set our polynomial equal to 0. And I know what you're thinking. Let's factor, because that's what we did in the last 2. Absolutely. Let's give it a try. I'm going to go over here to the side. Out of my first 2 terms, I can factor out an x squared. Out of my second two terms, they don't have any common factors. So all I would really be able to do would be to write it as a factor of 1. And what's left behind is exactly the same as what I started with. Oops, 33 there. And you'll notice this time factoring by grouping did not work because this and this, those two factors do not match. So we are not able to factor this one using our traditional factoring techniques. So that's when we need to use that rational root theorem that we learned about. The rational root theorem gives us a procedure where we're going to make a list of possible solutions, and then we are going to test those solutions to see which ones are actual zeros of this polynomial. So for the rational root theorem, we start out by making a list of factors. In our textbook, they call it C. C is the factors of your constant. So in this case, it would be the factors of -33. We always want to include both the positive and the negative version of any factor we're going to list. So 33 could be 1 times 33, or it could be 3 times 11. And those are all the factors for 33. And then we also make another list, and in our book they call it D. D is a list of the factors of your leading term, the coefficient of your leading term. In this case, our leading term, or the one with the highest exponent, is x cubed, and the coefficient is 1, so our list is not much here, it's just plus or minus 1. Okay, our final list of possible solutions to this equation, we take everything from list C and divide it by everything from list D. This case, it's not too interesting because when we divide by 1, we just get the same number back again. So I'm just going to rewrite our original list here. Sometimes when I rewrite it, I like to put it in numeric order because I usually start with the smallest values when I'm going to be testing. So this is our list of the possible rational zeros of our polynomial. Now, to figure out which one of those might actually be a zero, we have to test them either by plugging them into the equation and looking for an answer of 0, or by doing synthetic division and looking for a remainder of 0. I usually like to just plug them into the equation. So I'm first going to test x equals 1. So you can do this by hand, you can do it on your calculator, you can do it in your head, but what we're doing is we're putting 1 in place of x. So we'd have 1 cubed minus 11 times 1 squared plus 35 times 1 minus 33. And we want to see what that's equal to. This is a good opportunity, if you have it, if you have a multi-view calculator, to use that table button. And I'm going to show you how to do that real quick. If you hit your table button on your calculator, you can see you get y equals, and you can type a function in here. So we're going to type that function from our problem, which was x cubed. So to get an x, it's this button right next to the number 4, x, and then our exponent key cubed. Then we use our arrow to get out of the exponent, minus 11. We use that x button again, squared, plus 35x minus 33. And then we hit enter. And on this page, all you need to do is use your arrows to go down to ask, because we want it to ask us our x values. We want to be able to specify what x values we want to put on our table. And then we go use our arrow down to OK and hit enter. And now we have basically a t-table. So if I want to plug 1 in for x, I type 1 in the x column and hit enter. And I can see that my y value, or my function value, is -8. This is kind of a quick way to test a bunch of values. So now I can plug in -1. So I would go back to my calculator. I hit -1, enter, and I find out that my function is equal to 80 at -1. Remember, I'm looking for an answer of 0. That's the one that will tell me I have one of my possible solutions, or one of my solutions. Next up, I'll test 3. So I hit 3 and enter. And look, there it is. Ding, ding, ding. That's what I'm looking for. I'm looking for an answer of 0. So that tells me that x equals 3 is one of the solutions to our equation. Now, if you don't have the multi-view calculator, you can absolutely just type each one of these in on your calculator to get the answer. You don't have to have a multi-view. Okay, so once we find one of our solutions, we want to use that answer to reduce our original polynomial. So we're going to take that original x cubed polynomial, and through synthetic division, we are going to reduce it down to a quadratic. So we put our solution over here in the box, setting up for synthetic division. Then we write our coefficients. We had 1x cubed minus 11x squared, 35x, and negative 33 was our constant. So for synthetic division, we drop down that first number, just bring it down, and then we multiply 1 times the number in the box. 1 times 3 is 3. Then we add. Then we multiply times the number in the box. Then we add. Then we multiply by the number in the box. And then we add. You should get a 0 here if you got a 0 here. That's just a check. What we really want to take away here are these new coefficients. Since we started with a cubic polynomial or a 3 exponent, we now have a squared polynomial. So now I can solve this polynomial. It's a quadratic. I could try to factor it. I happen to know this one's not going to factor with that 11 back there. So I need to solve this one using the quadratic formula. So we go ahead and plug in x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. We go through and start simplifying. That minus a negative 8 becomes a positive 8. Negative 8 squared is 64, and 4 times 11 is 44. So we can do the subtraction under that radical. Then we can simplify that radical. The square root of 20 simplifies to 2 times the square root of 5. And then finally, we can cancel. If you're going to cancel the 2 and the 8, remember you have to cancel that 2 with both terms. Don't just cancel it in one place. So we end up with 4 plus or minus the square root of 5. So our solutions, our zeros for this problem are 3, that was the number we found earlier up here, and then 4 plus the square root of 5, and 4 minus the square root of 5. That's part of our answer, our solutions. This problem also asked us to use those solutions to factor that polynomial, okay? So each solution leads to a factor, and the factor is always x minus c, where c is your solution. So this 3 goes to the factor x minus 3. This next one would go to the factor x minus 4 plus the square root of 5. And then this last one would go to 4 minus the square root of 5. You could simplify some signs in there if you like. This is not a traditional way to factor things. An acceptable answer would also be the x minus 3, and then that quadratic equation that we had after we reduced our polynomial, because we typically only factor over the rational numbers, not over the irrational or the square roots, okay? So either one of these would be an acceptable answer. This is the one we're more used to seeing for a factorization. Okay, next up, number 4. Now we're moving on to I said rational. I meant radical back here. Radical, not rational. Those are radicals. Sorry. Those are words. Next, now this is a rational equation, a rational function, and it asks us to find our vertical, horizontal, and oblique asymptotes, okay? Before we start finding asymptotes, we should take a look at the original function and see if it can be reduced or simplified in any way. So we want to start off by factoring. Okay, the top can't be factored. That just stays 5x squared. But the bottom, we can do some factoring there. That's a nice little trinomial that will factor. X squared becomes x times x. And then we're looking for factors of 20 that will add to negative 12. So if we take 2 times 10, that definitely gives us 20. And if we make it a negative 2 and a negative 10, that gives us the negative 12. It also gives us our positive 20. So there is our factored form of our rational function. It turns out nothing can be canceled, nothing can be simplified. So we'll just keep going from there with our asymptotes. For vertical asymptotes, we take our denominator and set it equal to 0. So we might as well go ahead and use the factored form because we would have to factor it anyway to solve it. So if we set x minus 2 equals 0, we get one vertical asymptote at x equals 2. Or it could be that x minus 10 equals 0, so we get another vertical asymptote at x equals 10. Remember that asymptotes are lines. So if you're asked for a vertical asymptote, you don't want to just write 2 in the blank. It's x equals 2. That's the equation of a line. So you want to write that entire equation as your answer for a vertical asymptote. To look for a horizontal asymptote or an oblique asymptote, kind of all in one process, what we do is we look at the degree of the top and the degree of the bottom of our rational function. So the degree is the highest exponent you see. And you can see that the numerator, the top, has a x squared in it. So its degree is going to be 2. The denominator also has an x squared in it. So its degree is also 2. Whenever those degrees match, that means we are going to have a horizontal asymptote. It's going to be y equals a over b, where a and b are the leading coefficients of your numerator and your denominator. So that means we're looking for the highest exponent and then take the coefficient in front of it. So for the top, well, there's only one term. That is our leading exponent, our leading coefficient. So the coefficient is 5. In the denominator, here's our x squared, and the coefficient of that term is 1. So that means we have a horizontal asymptote at y equals 5. Anytime you have a horizontal asymptote, you will not have an oblique asymptote. It's one or the other, not both. Okay, next one has same direction, so we'll basically go through that same procedure. Again, let's take a look at it before we talk about asymptotes and see if anything can be reduced or simplified. We can factor the top. There is a greatest common factor there. And we can also factor the bottom. X squared into x times x. And negative 18, and I need a 7. How about a 9 and a 2 with a negative 9 and a plus 2? That works. Oh, backwards. I need a positive 7. I did those backwards. Always check yourself. Always check your work. So to get a positive 7, I need a plus 9 and a minus 2. There we go. And notice now I have a common factor on the top and the bottom. So I can go ahead and cancel that common factor. If this question asks, that would be where we have a hole, but this one doesn't talk about holes, so we don't need to worry about that. But this is the reduced version that we want to use for finding our asymptotes. So again, the vertical asymptote, we take the denominator and set it equal to 0. So we get a vertical asymptote of x equals negative 9. And then for our horizontal asymptote and oblique asymptote, we take a look at the degree. The degree of the top, in this case, is 0. There is no variable, so the degree is 0. The degree of the bottom, we have x to the first power, so the degree of the bottom is 1. Anytime the top number is smaller than the bottom number, or n is less than d, that means we automatically have a horizontal asymptote at y equals 0. And if we have a horizontal, we know that there is no oblique. Okay, next up with rational functions, we want to go ahead and graph one of these. Okay, so when you're asked to graph a rational function, the most important things are the intercepts and the asymptotes. Okay, we want to find intercepts and asymptotes, and then we'll see if we maybe need a few other points that we can get in a t-table. So let's start off by looking at our intercepts, our x-intercepts. Remember, x-intercepts are the same for any function. To find an x-intercept, you put 0 in place of y or 0 in place of f of x. Okay, to solve this little equation, we can multiply both sides by x minus 4. 0 times x minus 4 is still 0. And on the right-hand side, those x minus 4's cancel each other, and we just have 3. 0 equals 3. That is what we call a contradiction. That is not true. And what that tells us is that there are no x-intercepts for this graph. So there are none. Next up are y-intercepts. Y-intercepts are usually easier to calculate because you kind of do the opposite here. We put 0 in place of x. So it's typically just a calculation. You have to do 3 over -4, so that's -3/4. So that means that our y-intercept is the point 0, -3/4. Okay, intercepts, and now we're going to look at asymptotes. Again, similar to the last two, we'll start with that vertical asymptote. We take the denominator and set it equal to 0. That means we have a vertical asymptote at x equals 4. For our horizontal asymptote, oblique asymptote, to determine those two, we again look at the degree of the top. In this case, there is no variable, so the degree is 0. The degree of the bottom, we have x to the first power, so the degree is 1. Anytime n is smaller than d, that means we know we have a horizontal asymptote at y equals 0. Okay, so let's sketch in what we have so far. Let's start with those asymptotes because those are going to help us. They kind of work as guidelines for the rest of our graphing. So we have a vertical asymptote right there at x equals 4. We put our asymptotes in as dashed lines. We have a horizontal asymptote at y equals 0. And then let's see, what color do we want to use for our graph? How about light blue? We'll go ahead and plot that y-intercept that we found. That's the point 0, -3/4. I know fractions can be a little tricky to graph, but we just give it our best shot. About there, okay? 1 point. That is not enough for us to draw the rest of our graph. So at this point, we want to create a t-table to fill in some more points. And we want to choose some smart values for x. Technically, we could put anything we want in this column and do the calculation, but some values for x will be more helpful for us than others. So we already have this point where x equals 0. That's our y-intercept. So let's get some points between our y-intercept and our asymptote. So maybe x equals 1, x equals 3. You could use 2 also, 1, 2, 3, any of those work. So we'll take that and plug it into our equation. 3 over 1 minus 4, that ends up being -1. And 3 over 3 minus 4, that ends up being -3. So let's go ahead and plot those 2 points, see what else we have now. So 1, -1 is right there, and 3, -3 is right there. So you can see these 3 points we have chosen kind of set our curve there. And then from that point, we can use what we know about asymptotes to sketch out the rest of our graph. Because if we would pick x values like -1, -2, -3, and keep going in this direction, what's going to happen is our curve is going to get closer and closer and closer to that asymptote, but it's never actually going to reach it. So that asymptote, again, works kind of like a guide for that curve. And then the same thing is happening over here. We plugged in x equals 3. If we did 3.5 and 3.6 and 3.7 and we get closer and closer to that asymptote, we are just going to get some really big negative numbers. So our curve is just going to take a dive and go straight down, again, getting closer and closer to that asymptote, but never crossing it. Now, we are not done. This is only a portion of our graph. We still have this whole section over here to the right of our asymptote. So we need some more numbers in our t-table. We need to figure out what's going on the other side also. So we don't want to do positive 4. We don't want to use x equals +4. That's where our asymptote is. We know our function's not defined there. So maybe we'd want to pick some numbers like 5 and 7 and 9. Okay, you can pick any numbers on the right-hand side of your asymptote to help you figure out what's next. When I plug in x equals 5, that's 3 over 5 minus 4, I get y equals 1. When I plug in 7, you can do this on your calculator if you want. Oh, I lied. You don't get 1, silly. You get 3. 3 over 5 minus 4, that's 3 over 1. That would be 3. When you plug in 7, that's when you get 1. When you plug in 9, you get 3/5, which for the purposes of graphing might be easier if we put it as a decimal, 0.6. So let's plot those 3 points. 5, 3, about right there. 7, 1, right there. And 9, 0.6, again, a decimal, kind of hard to graph exactly, just give it your best shot. Connect those 3 points and then use your asymptotes as your guidelines to see what the behavior of the rest of your graph is. And there is our completed graph. Okay, for number 7, we are asked to find the inverse of a function. So when we find an inverse, basically what we do is we swap out our x's and our y's. Anything that was a y, or an f of x, becomes an x. Anything that was an x becomes a y. So first thing I'm going to do is rewrite this function, but right there where it was f of x, that's not good. Now going to be x. And right there where there used to be an x, that's now going to be a y. Everything else stays the same. And then I solve for that new y, and that's going to give me my inverse function. So the first thing I want to do here is add 2 to both sides. So I get x plus 2 is y minus 3, quantity to the 5th power. Okay, keep in mind I'm trying to solve for y. Right now, y is trapped inside of that exponent, so I need to get rid of that exponent. We get rid of an exponent by using a radical. So to get rid of the exponent of 5, I will take the 5th root of each side of that equation. So then I end up with the 5th root of x plus 2 equals y minus 3, because over here the radical and the exponent canceled each other. And then the final step will just be to add 3 to both sides. So we end up with the 5th root of x plus 2 plus 3 equals y. You can leave it like that. Our inverse function, if we want to write it with function notation, is the 5th root of x plus 2 plus 3. Just make sure the plus 3 is not under the radical. Sometimes we write it in front just to be safe. Okay, next one is another inverse function problem. So we'll do same procedure here. Instead of instead of f of x, I'm going to put y there. Let me get it straight. How many times can I say it backwards? Instead of f of x, I'm going to put x. And then any place I had an x, I'm going to change that to a y. Make sure you change every x variable to a y, both the one on top and the one on the bottom. Again, next step is to solve for that new y variable. This one takes a few more steps than the last one. First thing you need to keep in mind is you can't solve for anything that's stuck in the denominator. Okay, so we have to get that 2y minus 5 out of the denominator. So I'm going to do that by multiplying both sides of my equation by 2y minus 5. On the left, I can go ahead and distribute, multiply that x through. So I have 2xy minus 5x. And on the right, those cancel each other, and I'm just left with the 3y plus 4. Keep in mind, we're solving for y. Okay, in order to solve for y, any term with a y in it has to be on the same side of the equation. Okay, so that's our next step. Gather anything that has a y on one side, and anything without a y goes to the other side. So I'm going to move this 5x over to the right. And I'm going to bring this 3y to the left. So all the y's will be on the left together. Okay, when I do that, I have 2xy minus 3y. And on the right, I have 4 plus 5x. Okay, solving for y. So I need one single y if I'm solving for y. Right now I have it in 2 separate terms. So I'm going to factor that y out front. Okay, now I have y times a factor, y times a quantity there. So to solve for y, I divide both sides by that quantity. So here's my final answer, y equals 4 plus 5x over 2x minus 3. Or if we were to write it in function notation, f inverse of x equals 4 plus 5x over 2x minus 3. Okay, and one more in this video. Solve the equation, and we have here an exponential equation. We know it's an exponential equation because the variables are up in the exponents. Okay, so the easiest way to solve an equation like this is if we had matching bases. Right now, we don't have matching bases. We have a base of 64 on the left and 16 on the right, but 64 and 16 can be rewritten so that they are matching bases. So we are looking for a base that I can raise to the x to an exponent to get 64. And the same base can be raised to a different exponent and get 16. And it turns out that 64 is equal to 4 to the third power. And 16 is equal to 4 to the second power. If you can't come up with these, you might just have to play around on your calculator, a little trial and error. Try some numbers. Try 2 to the second, 2 to the third, 2 to the fourth. See if you get anywhere. Try 3 and raise it to several exponents and see if you get anywhere. But this is the substitution that's going to work best for us. So now we go ahead and rewrite this. 64, instead of 64, I'm going to write it as 4 cubed. But that exponent has to stay on there. 64 is raised to the 3x plus 2 power. And on the other side, instead of 16, I'm going to write that as 4 squared. But again, we have to keep that exponent on there. 16 is raised to the x minus 1 power. And now we have matching bases. And since exponential functions are one-to-one functions, what that means is we can just grab these exponents and set them equal to each other when the bases match. So over here, we get 3 times 3x plus 2. And over here, we get 2 times x minus 1. That's a pretty basic equation to solve. We can distribute on the left and distribute on the right. And then let's move some terms around. Let's take this 2x over here. And let's move the 6th over there. So we end up with 7x equals negative 8. Divide both sides by 7. And we get x equals negative 8 over 7. There's our solution to that exponential equation. And that's it for our first video.